chains, the polymer chains in a particular product, you may also be able to improve the mechanical performance of that material, and so get the same performance of an item you molded from oriented polymers, and use less material. So that's another good way of saving material. And here's another one. What about using structural polymer foams? I think you may have already heard something from a company dealing in that sort of area. And here's an example of that. So this is Mucell, which is a Zope Foams company. And they've discovered a way of foaming the material at the end of an extruder. So they're using supercritical fluids, which they introduce to the polymer in the melt, and they make a foam. On the top right there, you can see the structure of the foam with the cells. They're about 100 microns across, and they're reporting material savings of 15 to 20%. There is a bit of energy involved, of course, in creating the foam, and so it's a trade-off as to whether this is worth doing. But I would have thought with a 15 to 20% saving, it was well worth considering in many applications. So what we've done is we've tried to collect changes or improvements in energy, and that's the ones on the left-hand side of this Venn diagram, and also changes which involve reductions in material use, and that's on the right-hand side. But actually in the middle, there's also another category, which is where we do both. And this can be particularly effective. It involves a bit of collaboration between the material suppliers and the process people. But here's a couple of examples of those. So this is a biaxially oriented polymer pipe system. So by introducing the biaxial orientation, you can improve the mechanical properties of the polymer and the pipe. And so the pipes can have thinner walls for the same properties, the same mechanical performance. So you're saving material, and you're also saving energy in some of the use of this pipe in transportation, because it's lighter, and actually the fluids flow better inside this pipe as well. So a very good example of the double gain there in terms of both material and energy. And here's another one. It turns out that some chemistries of thermoplastic you can produce in very low viscosity form. So you can pump things into molds, and they continue to polymerize when they're in there to form a proper thermoplastic at the end, a high polymer. And so you're gaining in terms of energy saving during processing, because it's a lower viscosity material, and also it's fully recyclable at the end of life. So you gain twice, which is, again, a very good example of what we're trying to do with this project. So what does all this mean in terms of, for example, polymer selection and sustainability? Well, it seems to us in this project that here we are in 2022. If you were looking to try to make a new product and you wanted to select the right polymer, of course, it needs to be price and performance satisfying. So that's the first thing. But now, of course, we have some degree of circularity considerations. How recyclable is the polymer? And also, is it energy efficient, based on what I've just said about the energy efficiency side of life? Energy is becoming more and more expensive, so you can gain money savings as well as sustainability savings. But there may be trade-offs, just as Amy was saying at the beginning of this talk. You may have to make hard choices about this trade-off between being really energy efficient and being circular. So I think more and more we'll see debates in this area as we go forward. So our conclusions so far from our project are as follows. There's an awful lot of research aimed at improving sustainability, so making polymers more recyclable and so on. There's much less R&D going on in terms of energy and materials efficiency at the moment in processing plastics. There's, in general, less embodied energy in most engineering plastics compared to other engineering materials, which is great, but there's still plenty of scope for further energy savings, and you know, a few tens of % is certainly possible, we believe. Many energy saving techniques are out there. Some of them will involve some investment. The price of energy, perversely, might drive change quicker in that particular area. And there are also an increasing number of areas where simultaneous changes to both material and process will be very, very beneficial. So we look forward to more of those coming through in due course. Now, I did mention that this project is a work in progress. So if there are people out there with further examples that they'd like to send to us for inclusion into our report, which is due out in April, I'd be really pleased to receive those. These are my contact details, but if you can't find me, then please send them to Sally Becken and she can forward them on to me. Thank you very much for listening, and that's the end of my talk.
Great, thanks, Roger. That's a super introduction there, just really giving the scale of some of the savings that some people in manufacturing can make, and really glad to see kind of the importance of those resource efficiency savings. As you're saying, if you can avoid processing some material in the first place, the amount of energy to be saved there it can be often far greater than if you're just sort of tinkering around with just energy efficiency within the plant itself. I've just got one quick question for you before I let you off the hook for a few minutes. If you were a manager of a factory manufacturing products from thermoplastic and you wanted to reduce energy usage, what is the first thing you would do, given that you've given us lots of options there?
Yes, well, I think the very first thing is to understand the magnitude of the savings. So in other words, start to look for ways to measure the energy that you're consuming in your particular processes and your particular polymers. And then that sets the base level from which you can then improve. So I think that's a very first step. And that's what I would suggest people do. Robin Kent's been doing it for a very long time. He'd be one good place to go to or read his book. But there are others around as well, I'm sure. Great.
Yeah, well, thanks very much for that. So again, as I say, if anybody's got any questions specifically for Roger or just general for the whole panel, please put them into the Q&A as we're going through and we can pick those up again at the end. So thanks, Roger. Hopefully come back to you shortly. Great. So now we're going to move on to Richard Platt. Richard works for E4Tech and he co-leads on their work in low carbon fuels and sustainable chemicals. So Richard, I will leave it over to you to give a good overview of some of the advice you've got in this space. Thank you.
Thanks, Amy, and very interesting presentation, Roger. So I'm going to switch focus a little bit and talk about the fossil oil and gas that currently dominates the makeup of polymers and plastics and options for replacing that with renewable, with circular carbon, and how that fits into reaching net zero. So as we know, the chemical sector is the major provider of products to the polymers and plastics sector. And I'm showing this because this shows the lack of progress that the chemical sector has made towards net zero. It is the sector with the least amount of targets set aligned with a Paris temperature rating reduction. And, you know, there's reasons why that's happened. You know, there's multiple complex processes. The use of fossil fuels as both feedstocks and energy, and the complexity of the varying end of life options for plastics, one of the major applications of chemicals. So why is it important to avoid virgin fossil carbon in the polymer supply chain? So if we think about oil and gas and its uses, chemicals and then plastics are the largest industrial user after fuels. And about a third of that oil and gas get used as energy to make the chemicals. And then about a third of 2/3 of it ends up actually in the molecules and then in the plastics, which, you know, are a large portion of chemical use. So depending on that end of use, end of life of plastics, that carbon locked up in the molecules will then come out into the atmosphere and contribute to global warming. So finding solutions to reduce that fossil carbon going in to chemicals and then into polymers is crucial for meeting net zero. So today, you know, as we all know, oil and gas is extracted, chemicals are made, polymers are made, plastics are made, and then are used and end up in generally undesirable places, either incinerated, landfill, littered, or in some places recycled. So what are the options we can consider? There's mechanical recycling, and that works with some polymers, and it's a very good way to, when it works, to reduce the amount of fossil carbon that we extract and keep the carbon in a loop. But there are challenges around this, downgrading, contamination, mixed plastic streams, small volumes of some plastics that are hard to recycle. Emerging chemical recycling routes are, options for the hard to recycle plastics, but there's various levels of, actual losses, and the actual amount of carbon that's kept in the loop and recycled varies quite considerably between different chemical recycling technologies. And it's also requires additional investment and infrastructure, which is required to build this up. So the third option is integrating biomass into the value chains, taking out fossil chemicals and replacing that with bio-based chemicals. Now, this is potentially could lead to carbon neutral or negative emission polymers, but there's challenges with supply in terms of competition with fuels, and also there's considerations around sustainability, land use change based on the bio feedstocks that supply these routes. Another option is either captured CO2 from point sources or from the atmosphere, and combining this with low carbon hydrogen to produce chemicals and displace those fossil-based chemicals that are supplying the value chain today. So these are the range of categories or options for replacing that carbon in the molecules. And then, of course, there are options for reducing the emissions in the processing. Some of the things that Roger spoke about, and also other options around electrification, bioenergy in the actual energy required to process and make the products. I'm going to dive a little bit into different types of recycling. So this diagram shows on the bottom the linear value chain from oil and gas right through to plastic products. And then in the green boxes, we're showing the different types of recycling. The traditional mechanical recycling on the right-hand side, purification, then decomposition, so breaking down plastics to monomers, and then conversion, thermally breaking polymers to similar inputs as feedstocks, again, and rebuilding them into polymers. And on a very high level, if you look on the left-hand side, those processes require more energy, firstly to break down the waste plastic, and then also to reprocess it to products. Whereas the options such as mechanical recycling on the right are less energy, so and keep more carbon in the loop. So at a very high level, we're aiming for the right-hand side, but there's obviously challenges around whether the right-hand side is possible for all streams or not. And it's worth saying that mechanical recycling, obviously a quite mature technology, some conversion technologies such as pyrolysis, an old technology, but it's been applied quite widely now today. But the options in the middle are less mature, but could be interesting options that are better on a GHG basis than some of the pyrolysis options being developed today. So I'm now just going to take a quick case study to talk about one polymer value chain and the things that are happening, actually, some of them today and some of them being researched at the different levels of commercialization, that may change the overall impact of this value chain. So firstly, so the value chain we're looking at is polyurethane, and one of the obvious options is polyurethane, and the chlorine, with chlorine going into it, is using renewable electricity. For ammonia, there's a lot of work going on to convert ammonia production to using renewable hydrogen from electrolysis, moving away from natural gas. There's research going on by companies to find replacements for benzene or nitrobenzene and aniline going into isocyanates. There's some biopropylene available in Europe, produced from biopropane. There's already bio-based polyols and CO2-based polyols on the market. And there's companies looking at end-of-life polyurethane, for example, mattresses, and how you could recycle that polyurethane foam back to polyols. So very quickly, how are E4Tech working on this, and how we're helping? One way we're working this, we're helping people to understand, clients to understand these systems. So which options can help decarbonize? Which options are most feasible? When are they available? What do they cost? What is their impact on GHGs over the system? What are the opportunities and challenges related to them? So key takeaways: polymers and the polymer value chain is the largest industrial consumer of oil and gas. So it's important to think how we can accelerate the reduction, accelerate other options than using oil and gas as the main feedstocks. There are three main options to do this. Reducing, incorporating bio options, recycling, or incorporating captured CO2 and renewable or low carbon hydrogen. These range in maturities. Some are very mature and available on the market today, but they generally represent a small portion of the overall product flows. And some are early stage and in the process of being scaled up. There's a lack of understanding of how these options actually would contribute, or wouldn't in some cases, to reducing emissions and those system impacts. And that's an area where we're focused to try and understand those impacts and which options, or which suite of options, need to be deployed in the coming years to help reach net zero. Thanks.
Great, thank you, Richard, for that. Really some interesting points in there. I'm glad you mentioned tools at the end there. That's my pet topic, that sustainability tools. So just interested to know that tool you're talking about, is that one that you would expect manufacturers to use themselves to look at options, or is it more for kind of looking at the industry in general as to kind of where they should find the best options for changing whole supply chains?
No, I think it can be both. So some background, we do work for individual clients and we do work for governments. So there could be both those options. It would depend on how it's done. We have developed a tool looking at different options for a chemical company, a chemical and polymers company, thinking about those options for them. But it could be a wider systems tool that considers regions or countries as well. Yeah. Okay, great.
I mean, when we think about sort of someone looking at sort of integrating renewable or circular carbon, what do you see kind of being as the sort of the biggest barriers to doing that, and how could they be overcome? If that's not too big a question.
Yeah, I think it's important. The number one barrier is probably always stated as cost. This is going to cost us more than and therefore the kind of action around that is okay. Well, there has to be a situation where there's a business case, and how do we understand if